So today we are going to discuss about the Compton scattering, or in general way Compton effect. So in this topic we are going to discuss about how the quantum effect challenge the classical physics, that is light cannot behave as a particle, and this experiment is basically the evidence which proves that light also behaves like a particle. So before discussing about the Compton scattering, we should know about what are the light, what are the characteristics of light, and what is wave particle duality. So in the next slide we are going to discuss about the wave particle duality, which is the prerequisite before studying about the Compton scattering. So before discussing about the Compton effect, we should know about the dual nature of matter and radiation. So what are the characteristics of light, or you can say radiation, because light is a small part of electromagnetic radiation. That's why in general way we are using radiation, but the portion that we can see from the naked eye is called as light. So basically light has a character of wave as well as particle. This behavior of light is called wave particle duality. So when we are talking about the wave nature, we are very distinct about the wavelength and amplitude. So basically the wave nature is characterized by lambda, that is wavelength, and amplitude, which is represented by capital A in general. And secondary, when we are going to represent the light as a particle, then for particle we are very specific about the energy and momentum. So these two are the characteristics of particle, which is energy and represented by capital E, and momentum, which is represented by small p or sometimes capital P. So this wave particle duality follows the quantum world, because according to classical physics this wave particle duality is a non-valid, invalid concept. But when we are going towards the quantum mechanics, so wave particle duality, black body radiation, these are the some facts that governs the wave quantum mechanics, by the quantum mechanics. And since we know that wave particle duality exists, because we have evidence and the following experiments which proves that light acts as a wave nature, and also it reveals the particle aspects. So as initially it is believed that only light has the wave particle duality, but when Davis, Germer and de Broglie came into the picture, then they have proved that not only light but also the matter also possesses wave particle duality. So that wave particle duality concept is universal, and it is not restricted to radiation only. So thus matter also possesses dual nature, and it shows wave particle duality. So these are the some basic concepts which we should know before studying the Compton effects. So in this slide we are going to visualize the concept of Compton effect. So as you can see, when the photon of wavelength lambda strikes with an electron which are at rest in the laboratory frame, then the photon which strikes with electron scatters away from its original position, while the electron receives an impulse and moves away also. So that change in wavelength, because we are considering the incident photon wavelength is lambda, and the change in wavelength is lambda dash. So with the help of Compton effect we are able to find the change in wavelength lambda dash minus lambda is equals to, we found, h upon mc 1 minus cos theta, where theta is the angle between the incident photon and scattered photon. So in the actual the X-ray photon is used in the actual experiment of Compton effect. The X-ray photon is used, and that electron it is actually there is a material is used. So in that material we have consider, suppose that electron is at rest, and we are actually focusing on the scattering of X-rays, because after scattering the frequency reduces. or you can say the energy reduces, because energy is proportional to the frequency. E equals to h nu. So when the scattered photon has a less frequency, or if we are talking about in terms of wavelength, then the wavelength after scattering, the wavelength increases. So we can find out the change in wavelength by the following formula, and this gives the change in wavelength in respect to the scattering angle. So the scattering of photon by an electron is called the Compton effect. So in this slide we are going to explain and get the formula for the change in wavelength with respect to scattering angle. So we are going to reconstruct the whole experiment, and we are, by using the conservation principle and basic physical principle, we are going to get the relation of change in wavelength versus the scattering angle. So according to the quantum theory of light, photon behaves like a particle except for their lack of rest mass. So how far can this analogy be carried? For instance, we can consider the collision between a photon and electron as if both were a billiard balls. So the collision between photon and electron, or you can say the interaction between photons and electron, is such as that the elastic collision between two objects. Okay. So we are taking that analogy only, and initially we have considered that the photon as consider at rest as the electron is at rest in the laboratory coordinate system and is scattered away its original direction of motion, while the electron receives an impulse and begins to move. We can think the photon as losing the amount of energy in the collision that is same as the kinetic energy gained by the electron. So energy will be conserved, because what is happening in that experiment, Compton experiment, that electron, the incident frequency of the photon, or you can say the energy of the photon, is going to reduced after scattering. So that reduction in energy is given to the electron to increase its kinetic energy, because initially the electron is at rest. So now we are considering the initial photon frequency nu, and the scattered photon frequency is nu dash. So the loss in photon energy is h nu minus h nu dash, because h nu is the energy of the incident photon and h nu dash is the energy of the scattered photon. So how we can get the loss in photon energy? By reducing this. So h nu minus h nu dash equals to the gain in electron energy. So h nu minus h nu dash equals to the kinetic energy, and which kinetic energy it is, which is provided to the electron, because initially the electron is at rest, and when the photon is scattered, it transfers its energy to electron for providing its kinetic energy. Since the energy of a photon is h nu, its momentum is p equals to e by c, or e equals to h nu by c. Now I am going to explain this figure. So you can see the whole construction and its component, because it is very important to know the components in x direction and y direction to prove that relation, or to get that relation between lambda dash minus lambda equals to h upon mc 1 minus cos theta. So these are very important. So first we just discuss about the component part. So here this way you can see that incident photon is coming, which is having energy E equals to h nu and momentum h nu by c. Here it is a targeted electron. Okay, here it is the targeted electron which are at rest. So rest, that means their momentum p equals to 0 and E equals to mc square. Okay, because this is at rest. Okay, now here you can see when the photon strikes with the target electron, it is electron is also going to scatter, or electron is going to move. So after moving, the electron having energy E equals to root m square c to the power 4 plus p square c square, and the momentum of the electron p equals to p. Initially it is at rest, so we have considered the momentum p equals to 0, and then the energy is E equals to mc square. Now we already talked about the scattered electron energy and momentum. Now the scattered photon, we are talking about the scattered photon. So energy of the scattered photon E equals to h nu dash, and what its momentum P equals to h nu dash by c. So you can see that we are considering this direction, incident photon direction, we are taking this direction. So this is the reference direction. So the scattered electron is making scattered photon is making an angle phi from the reference of incident photon, and similarly the scattered electron is making an angle theta. So now we are going to discuss the components. So in the x direction, that incident photon have the component h nu dash by c, that momentum component, and what is the perpendicular component is h nu dash by c into sin phi. Similarly, that targeted electron has the momentum component in x direction is p cos theta, and in y direction is p sin theta. So now we have already discussed about the component part. So now we are going to do our calculation and apply the conservation principle. Okay. So now we are going to talk about the momentum, conservation of momentum and conservation of energy concept to get the our desired result. So why we are taking the conservation of momentum and energy? Because we are we have supposed that the photon and electron are interacting like a elastic scattering of a two object. When two object is colliding and the collision is elastic, then what are the changes? So we are going to apply the same principle here. So we know that according to the momentum, initial momentum, conservation of momentum principle, initial momentum equals to final momentum. So initial momentum, first we will talk about the x direction in the incident photon direction, and then we are going to talk about the perpendicular direction. So initial momentum equals to final momentum. So first in x direction, so h nu by c plus for electron, since electron is at rest initially, so the momentum will be 0. Now final momentum of photon h nu dash by c into cos phi plus that momentum of the electron in the direction x, so p cos theta. Now second thing, the perpendicular direction. So again apply the conservation of momentum. So initial momentum equals to final momentum. So after collision in y direction, photon component, there are no photon components, so 0, and equals to h nu dash upon c sin phi minus p sin theta. So this is for photon momentum after scattering and in the y direction, and this is for electron momentum. Since minus sign representing the, since photon direction is upper half plus direction, and that electron y direction is minus y direction, so that's why we are taking negative sign. Now we have all the formulas. So the angle phi is that between the direction of initial and a scattered photon, and theta is that between the direction of initial photon and recoil electron. Okay, so from all the equation, we just find out the formula that release the wavelength difference between initial and scattered photon with the angle phi between their direction, both of which are readily measured quantity, unlike the energy and momentum of required electron. So what we are going to get, we are just going to eliminate the energy term and for electrons, and we are going to derive a formula for momentum and that scattering angle. Okay, so first simplify all the formulas. So pc cos theta equals to h nu minus h nu dash cos phi, and pc sin theta equals to h nu dash sin phi. Okay, so just squaring and adding these two equations, we will get p square c square. So in the next slide we are going to do that. So by squaring each of these formula and adding the new ones together, the angle theta is eliminated, leaving p square c square equals to h nu over whole square minus 2 h nu dash into cos phi plus h nu dash whole square of h nu dash. The total energy of the particle is E equals to kinetic energy plus rest mass energy mc square. So E equals to root m square c to the power 4 plus p square c square. This is for electron. So kinetic energy plus mc square whole square equals to m square c to the power 4 plus p square c square. So from this, when we are going to simplify this, we got p square c square equals to k square plus 2 mc square into k. Now from the initial equation, kinetic energy equals to h nu minus h nu dash. So we are going to compare both the thing, and we got p square c square equals to h nu whole square minus 2 h nu into h nu dot plus h nu dot whole square plus 2 mc square h nu minus h nu dot. So substituting this value of p square c square in equation 2.18, we finally obtain 2 mc square h nu minus h nu dash equals to 2 h nu into h nu dash 1 minus cos phi. This relationship is simpler when expressed in terms of lambda. So dividing equation 2.20, this equation with 2h square c square. So mc by h nu by c minus nu dash by c equals to nu dash upon c square 1 minus cos phi. After simplifying this, we got lambda dash minus lambda equals to h upon mc 1 minus cos phi. So this is our desired equation, and this equation was derived by Arthur H. Compton in early 1920s, and the phenomena it describes, which he was the first to observe, is known as the Compton effect, and this is the experimental evidence to prove the quantum theory of light. In the previous equation, the equation gives the change in wavelength expected for a photon that is scattered through the angle phi by a particle of rest mass small m. This change is independent of the wavelength and of the incident photon. The quantity lambda c equals to h upon mc, that is here the quantity h upon mc is called Compton wavelength, and it is represented by lambda c. For an electron, lambda c equals to 2.426 into 10 to the power minus 12 meter, which is 2.426 picometer. Okay. So in terms of lambda c, the equation 2.21 becomes lambda dash minus lambda equals to lambda c 1 minus cos phi. So this is the final expression where lambda c represented the Compton wavelength, which is equals to h upon mc. So the Compton wavelength gives the scale of the wavelength change of the incident photon. Means if we have the Compton wavelength, it gives how much the wavelength changes and with respect to the incident photon wavelength. So we know that the greatest wavelength change possible corresponding to phi equals to 180, because after when we are substituting phi equals to 180, we got 2 times of lambda c. Okay, so this is the maximum possible change correspond to phi. Okay. So in general, when I have visualized the whole concept, I am using the colorful light, that is yellow and red, that is only for the symbolic representation that color is changing, that means wavelength is changing. So yellow has less wavelength than the red. So scattered photon has red wavelength, that means after scattering the wavelength is going to increase. But in general, the Compton effect is the chief means by which X-rays lose energy when they pass through the crystal or matrix.